Maria. I will be online, so if you want something, you can type me. So, Maria, the floor is yours. Thank you.
Thank you. Hello, welcome to our tutorials. We will start with the first one, the tutorial on Sentinel-1 SAR processing. The objective of this tutorial is to learn how to process Sentinel-1 synthetic aperture radar data through a Snap Python API. You will be introduced to the Sentinel-1 mission and its characteristics. Moreover, the use of Snap, a Python module that allows you to access the Snap Java API and process Sentinel-1 data in a Python programming environment will be demonstrated. First, we are going to make an introduction on Sentinel-1 mission. Sentinel-1 mission is formed by a constellation of two satellites, Sentinel-1A and Sentinel-1B. They are passing at a polar orbit faced at 180 degrees to each other to improve the temporal resolution of the system. They carry a synthetic aperture radar, which is an active sensor emitting radiation in frequencies of the C-band, and the mission provides data in a cycle of 4 days at the equator and with different imaging modes. While Sentinel-1A remains fully operational, Sentinel-1B sensor has not been working properly since December 2021, and it is planned to be replaced with Sentinel-1C within 2023. The Sentinel-1 mission includes a C-band synthetic aperture radar operating in 4 exclusive imaging modes with different resolutions down to 5 meters and coverage up to 400 kilometers. It provides dual polarization capability, very short revisit times, and rapid product delivery. For its observation, precise measurements of spacecraft position and attitude are available. Synthetic aperture radar has the advantage of operating at wavelengths not impeded by cloud cover or lack of illumination, and can acquire data over a site during day or night time under all weather conditions. So the Sentinel-1 has 4 acquisition modes and polarizations available, which are the strip map. It is a standard synthetic aperture radar imaging mode where the ground swath is illuminated with a continuous sequence of pulses, while the antenna beam is pointing to fixed azimuth and elevation angle. Strip map mode is used on request mainly for emergency management. Data products are available in dual polarization or single polarization. The main operational mode, interferometric wide swath, features a wide swath of 250 kilometers with medium geometric resolution of 20 meters for level 1 product and radiometric resolution suitable for most applications. The data are acquired in 3 swaths using the terrain observation with progressive scanning SAR imaging technique. In interferometric wide mode, pairs are synchronized from pass to pass to ensure the alignment of interferometric pairs. Interferometric wide is Sentinel-1 primary operational mode over land, and its data products are available in dual polarization or single polarization. In extra wide swath, the data are acquired in 5 swaths using the top SAR imaging technique. Extra wide mode provides very large swath coverage at expense of spatial resolution. It is mainly used for sea ice monitoring services and maritime surveillance with the capability to cover 400 kilometers wide area at its data tape. Its data products are available in dual polarization or single polarization. Finally, in wave mode, data are acquired in small strip map scenes called vignettes, situated at regular intervals of 100 kilometers along track. It is Sentinel-1's operational mode over open ocean, and its data products are available in single polarization only. Now let's continue with the polarization scene. Polarization refers to whether the radar signal is being measured in the horizontal or vertical plane. Polarization is a property of transverse waves, in other words, waves oscillating perpendicular to the direction of energy transfer, that specifies the geometric orientation, horizontal or vertical, of the oscillations. Over land, the same sharp polarization scheme is systematically used over a given area to guarantee time series of data in the same conditions for routine operational services. Depending on the area and the application, the selection is either vertical or horizontal. As a general principle, the polarization scheme uses the following logic. Dual polarization is used for monitoring of polar environments and sea ice zones, and VV polarization is used for all other observation zones, including land outside of the poles. An overview of the current Sentinel-1 observation plan in terms of acquisition mode and polarization is shown on this map. Next, the Sentinel-1 data products are made available systematically and free of charge to all data users, including the general public, scientific, and commercial users. The data are within an hour of reception for near real-time emergency response, within 3 hours for near real-time priority areas, and within 24 hours for systematically archived data. All data products are distributed in the Sentinel standard archive format for Europe, SAFE format. Each mode can potentially produce products at SAR level 0, level 1 single look complex, level 1 ground rates detected, and level 2 ocean. Data products are available in single polarization for wave mode and dual polarization or single polarization for strip map, interferometric wide and extra wide modes. The SAR level 0 products consist of a sequence of flexible dynamic block adaptive quantization compressed and focused SAR data. For the data to be usable, it will need to decompress and process using a SAR processor. Level 1 data are the generally available products intended for most data users. They are produced as single look complex and ground rates detected. Level 1 single look complex products consist of focused SAR data which are georeferenced, using orbit and attitude data from the satellite and provided in zero Doppler slant range geometry. The products include a single look in each dimension using the full transmit single bandwidth and consist of complex samples preserving the phase information. Level 1 ground rates detected products consist of focused SAR data that have been detected, multi-looked, and projected to ground rates using an Earth ellipsoid mode. Phase information is lost, and the resulting product has approximately square spatial resolution pixels and square pixel spacing with reduced speckle at the cost of worse spatial resolution. Ground rates detected products can be in one of three resolutions: full, high, and medium. The resolution is dependent upon the amount of multi-looking performed. Level 1 ground rates detected products are available in medium and high resolution for interferometric wide and extra wide modes, medium resolution for wave mode, and medium, high, and full resolution for strip map mode. Level 2 ocean products include components for ocean's well spectra, providing continuity with ERS and ASAR wave and two new components, ocean wind fields, and surface radial velocities. Now let's continue with the naming convention. We can extract important information from the file name of each dataset. Specifically, the first three digits identify from which satellites the data were acquired, which will be either Sentinel S1A or S1B. And next is the mode beam, which identifies the S1 to S6 beams in the case of strip map products. Otherwise, the acquisition mode is defined. The product type is defined in the third part of the file name, which can be raw, single loop, complex, and ground range detectors, or OCN. Next, the next digit is the resolution class, which can be full, high, or medium. Also, the processing level is defined with 0, 1, or 2. Next is the product class, which can be standard or annotation. Annotation products are only used internally by the payload data ground segment and are not distributed to the users. Next is the polarization, which can be single HH polarization, single VV polarization, dual HH-HV polarization, or dual VV and VH polarization. Next, the 14 digits represent the start date and time, and the following other 14 digits show the stop date and time. Next is the absolute orbit number, the mission data take ID, and finally the product unique identifier, which is a hexadecimal string. Next is a naming convention example to understand better the situation. This is the dataset which we will use in this tutorial. It was acquired on September 8, 2022. It was acquired in interferometric wide. It is a ground range detected product with high resolution and VV-VVH polarization. So the dataset includes synthetic aperture radar data acquired over the Pilot 1 study area via various catchment, which can be seen here. Next, you can download the required dataset through the Copernicus Open Access Hub or the Umbrella application developed from NOAA. Here you can see a screenshot from the Copernicus Open Access Hub. The area of interest is defined on the map, and the search parameters are filled in to search the required dataset for this tutorial. And next, we can see the search results and the footprint of the dataset. Additionally, the parameter values to query the dataset through NOAA's Umbrella application are also provided. Next, we will continue with the main part of our tutorial. First, we have to load several Python libraries. Matplotlib modules are required for visualization purposes. The zip file library to read the Sentinel-1 data, which are stored in a zip file. OS and glob libraries to access data. Pandas library for data manipulation, and Python image library for image manipulation. Additionally, NumPy for scientific computation with arrays, and GDAL for geospatial data manipulation. The subprocess library is used to make external calls to the system. And finally, Snappy and JPy, which is the Snap Python app interface and the Python Java bridge, respectively. So the Snap architecture provides a flexible graph processing framework allowing the user to create processing graphs for batch processing and customized processing chains. The Graph Builder in Snap Desktop allows the user to graphically assemble graphs from a list of available operators and connect operator nodes to their sources. Graphs can then be saved and batch processed from the graphical user interface or from the command line. Snap.io data processors are implemented as graph processing framework operators and can be invoked via Windows or Unix command line using the GPF graph processing tool GPT, which can be found in the bin directory of your Snap installation. We can type in the Snap command line GPT-h to print a list of available operators. Here we can get this information by using the subprocess library, where we can see all the operators which are installed in my computer. Next, if we type GPT, the operator's names, -h, a short description of what the specific operation is for, and a description of the arguments and options of the tool are displayed. So you can see the parameters that the operator remove GRD border noise requires, the source option, the description of the operator, and also the template for making the graph. So now let's describe the SAR processing workflow to create Sentinel-1 SAR analysis ready data. For this tutorial, we will use the processing workflow proposed in Filipponi's paper Sentinel-1 GRD pre-processing workflow. The workflow is composed of 9 individual steps: read, subset, apply, orbit file, thermal noise removal, border noise removal, calibration, speckle filtering, terrain correction, and saving the final output as GeoTIFF file. First, we're going to read the dataset and extract some useful information about it from its file name. The dataset is stored in a directory named data. Next, we define 7 lists to store the extracted information. We can extract from the file name the sensing mode, the product type, and the polarization. Next, we read the Sentinel-1 dataset with the snappy product.io read product function. We can get from its output the name of the dataset, the dimensions, and the name of the bunch included in the dataset with specialized methods: get name, get scene raster height, get scene raster width, and get bud names. All the extracted information is stored in a data frame for better visualization purposes, as you can see here. Next, let's get a quick look of the dataset we are going to process. The zip file library has the ability to redirect zip files without unzipping them. Here we open the dataset, search its content, and find the quick look image provided in the Sentinel-1 dataset. Next, we open the quick look image and read and visualize it with the matplot library. As you can see in the quick look visualization, the data are not georeferenced. So let's proceed to the second step of the processing workflow, the subset. We're going to process a small part of the initial data focused on the area of interest. and to minimize the processing requirements. We are going to use the subset operator provided by Snap. We can define this subarea by defining the upper left corner pixel coordinates or geographic coordinates and the width and height in number of pixels. But as we saw in the quick look, the dataset is not georeferenced, and therefore we will define the subset area by defining its pixel coordinates in the image. So first we create a hash map to store the following parameters. Copy metadata, which is set to true to pass the metadata information of the initial dataset to the subset product, and the region, which includes the upper right pixel coordinates and the width and height of the subset. So next we create the subset with the snappy GPF create product function. Subset is the operator name in the first argument of the function. The parameters we defined in the hash map. And as one reads is the source file, the initial Sentinel-1 dataset. With the getBand names method, we can get the bands included in the subset image, which are 4 bands, amplitude and intensity for the two polarizations. Next, we follow with the function definition for visualizing the products created with Snap. The function has 2 arguments, the image product produced by Snap, and names of the bands we are going to visualize. We loop through the list with the required band names, and we read them with the read pixel method. In order to read the whole subset, we need to know the width and height of the subset, which can be found with the getRaster width and getRaster height methods. We define a one-dimensional floating type array with a dimension equal to the height by width of the subset to store the data output from read pixels method. And then we reshape the output array to 2 dimensions. For better visualization, we cut out the outliers based on 5%, which can be computed with the NumPy percentile function. Finally, the bands can be displayed with the IMShow method, which requires the band that to be displayed, the color map, and the minimum and maximum values to be displayed, which are defined to be the 5 and 95% respectively. So here you can see the results. From the subset process. And we continue with the apply orbit file procedure. So even though the satellite's orbit is fine-tuned, its location will drift over time due to atmospheric drag and solar winds and non-uniform Earth's gravitational field. Because of this drift, periodic adjustments are needed, usually by applying tiny rocket bursts. As such, it is important to have the most up-to-date orbital files, which tell us the precise position of the satellites. Satellites' precise orbit are determined after a few days and are available days to weeks after the generation of the product. The operator to apply precise orbit available in Snap allows to automatically download and update the orbit state vectors for each RC in its product metadata, providing accurate satellite position and velocity information. Here you can see the configuration for applying this operator. We only need to define that we want to apply orbit file and assign it to true. and define the input dataset, which is the output from the subset operator. Next, it is the thermal noise removal operation, which is fundamental step for a precise radiometric calibration of synthetic aperture radar data. In terrain observation with progressive scan Sentinel-1 data, thermal noises consist of two additive noise sources. The first is related to the antenna pattern, and the second to the scalloping noise, which varies along the azimuth direction. To remove this type of noise, you can use the remove thermal noise operator. Like the previous operator, we only need to assign the remove thermal noise parameter to true and define the input dataset to be the apply orbit product provided from the previous step. Here you can see that the bands are only 2 now. And here are the results. And we continue with the border noise removal. While generating level 1 products, it is necessary to correct the sampling start time in order to compensate for the change of the Earth's curvature. At the same time, azimuth and range compression leads to radiometric artifacts at the image border. The border noise removal algorithm, available as an operator in SNAP, was designed to remove low-intensity noise and invalid data on scene edges. This operator requires two parameters to be defined: the width of the border margin to be removed and the trim threshold to remove low-intensity values. And here are again the new results, and we continue with the radiometric calibration, which is the procedure that converts digital pixel values to radiometrically calibrated sharp backscatter. The information required to apply the calibration equation is included within the Sentinel-1 GRD product. Specifically, calibration vector included as an annotation in the product allows simple conversion of image intensity values into sigma no values. And here you can see the configuration of this operator. We have defined different conditions based on the polarization modes in order to define the correct parameters. And here it's again the new result. Then follows the spectral filtering. Spectral appears in SAR images as a granular noise due to the interference of waves reflected from many elementary scatterers. Spectral filtering is a procedure to increase image quality by reducing speckle. The refined leaf filter has been found to be superior with respect to other single product speckle filters for visual interpretation because of its ability to preserve edges, linear features, point targets, and textural information. So here you see we define again the parameters of the hash map. We define that the filter will be the leaf filter. The dimension of the filter will be 5 pixels, and we create the new image, the 3D the speckled image with the snappy GPF create product. We define the name of the operator, we include the parameters defined above, and the input image, which is the calibrated image produced in the previous step. And here again the results visualized. And we continue with the terrain correction. As you saw in the quick look image, the data are not georeferenced. Also, SAR data are generally sensed with a varying viewing angle greater than 0 degrees, resulting in images with some distortion related to side-looking geometry. Terrain corrections are intended to compensate for this distortion so that the geometric representation of the image will be as close as possible to the real world. Range Doppler terrain correction is a correction of geometric distortions caused by topography, such as foreshortening and shadow, using a digital elevation model to correct the location of each pixel. The Range Doppler terrain correction operator available in Snap implements the Range Doppler orthorectification method for geocoding SAR scenes from images in radar geometry. It makes use of available orbit state vector information in the metadata, the radar timing connotations, the slant ground range conversion parameters together with the reference digital elevation model data to derive the precise geolocation information. So the operator, as you can see here, allows us to select the image resampling method, which is set here to be the bilinear interpolation. We can also define the appropriate projection system, which is the well-known text shown here. The well-known text for each projection can be found in the ESA Snap GUI. If you click in the Range Doppler terrain correction and find and search based on the EPGS code, you can get the well-known text for the projection system you need. You can copy paste it and add it to your code. So again, you include all the parameters defined in the snappy.gpf create product function in order to get the terrain corrected image. Next, we have to convert the image from the unitless backscatter coefficient to decibels using a logarithmic transformation with a linear to from dB operator. And next we write our output with the snappy.productio.writeProduct function. And finally, here we will read the final result with the use of the GDAL library. The final product has two bands, the sigma naught VV and sigma naught VH bands. And here we perform a 95 contrast stretch for better visualization to remove the outliers. And here it is a visualization of the final output, which is the Sentinel-1 ARD product. And here it is the end of this tutorial. Thank you for your attention. Shall we make a 15 minutes break and we will continue with the Sentinel-2 tutorial. Okay, hello again. Let's continue with Sentinel-2 tutorial. Um, so, the objective of this tutorial is to learn how to process Sentinel-2 multispectral data with Python and GDAL library. We will start with an introduction about Sentinel-2 mission and its products, and we will continue with the processing of the data and the computation of various spectral indices. Sentinel-2 mission is formed by a constellation of two satellites, Sentinel-2A and Sentinel-2B. They are passing at a polar orbit phased at 180 degrees to each other. Each satellite carries a multispectral instrument which has 13 bands and frequencies of the visible near-infrared and short-wave infrared part of the electromagnetic spectrum. The mission provides data in a cycle of 5 days at the equator. It is characterized by the various spatial resolutions based on its spectral bands to 10, 20, and 60 meters resolution. Sentinel-2 data products are made available systematically and free of charge to all data users, including the general public, scientific, and commercial users. The data are available for users in two processing levels, Level 1C and Level 2A. Level 1C data are top-of-atmosphere reflectances in cartographic geometry, while Level 2A are atmospherically corrected, in other words, bottom-of-atmosphere reflectances in cartographic geometry. Now let's discuss about the naming convention. Where based on the file, from the file name you can extract important information, like the mission identifier, which denotes the satellite and will be either S2A for the Sentinel-2A or S2B for the Sentinel-2B satellite. And next we have the instrument identifier and the product level, which will be either L1C or L2A. The product start and date and time are shown as 14 digits to represent the date and time separated by character T. Next follows the payload data ground segment processing base length number, the relative orbit number, and the tile number, and finally the product discriminator. Next we have a naming convention example. For this tutorial we will use the following dataset. Based on its file name, we can conclude that the data are acquired from Sentinel-2A. The data are atmospherically corrected since we have level 2A product, and were acquired on August 27, 2022. The dataset includes multispectral data acquired over Lithuania, which is the area of interest for Pilot 2. You can download the required data through the Copernicus Open Access Hub or the Umbrella application. Here you can send screenshot from the Copernicus Open Access Hub, the area of interest defined on the map, and the search parameters required in order to find the dataset we need for this tutorial. Additionally, the parameter values to query the dataset through NOS umbrella application are also provided here. And so, for this tutorial, we will use the GDAL library, which is well known for its ability to read and write many different raster file formats and perform basic data processing functions such as reprojection and resampling. First, we have to load several Python libraries. The zip file library to read the zip file where the Sentinel-2 data are stored. Matplotlib and EarthPy modules are required for visualization purposes. Pandas library for data manipulation. Additionally, NumPy for scientific computation with arrays. And GDAL for geospatial data manipulation. The SkyPy library also is used for image processing, particularly for resampling the bands. So it is important to have a greater than 3.1 GDAL version installed on our system in order to have the ability to read all the available information included in the Sentinel-2 dataset. So we have here a command to check our GDAL version. Here I have the 3.5.2 version, so I'm okay to continue. So first we have to open the Sentinel-2 dataset with the GDAL open function. We have to pass as the first argument of the GDAL open function is the file path of the Sentinel-2 dataset required, and the second argument defines the access right if we want to read only the file or change it with the GA update. Next, with the get metadata method, we can get the metadata of our Sentinel-2 dataset, which includes the cloud coverage percentage, which here is 25%, the footprint defined in WGS 84 system, next, let's see the file structure of the Sentinel-2 file. Its Sentinel-2 dataset includes 3 different subdatasets based on their spatial resolution and an additional true color image for quick inspection of the data. The path and the description of each subdataset can be retrieved with the get subdatasets method. And here we process the output of get subdataset method to separate the metadata of each subdataset for easier manipulation. Here you can see a table with the path for its subdataset and its description. Here it's the 10-meter bands. This is the 20-meter subdirectory. The third row is the 60 meters bands and the true color image in the last row. And next you can get also the metadata for each subdataset. We open the subdataset with the GDAL open function again. we can fetch the projection with the get projection function, where here we can see that the data set is projected in UTM zone 35 north. We can also get the geotransform of the image, the origin, in other words, the upper left longitude and the upper left latitude of the image, the pixel size in the X and Y direction, and the width and height of the image. We can also compute, based on this information, we can compute the extent of the image based on the projection of the data. Next, we will discuss how to read Sentinel-2 bands, the full extent and partially. So to read a subset of the data set, first we have to define the region of interest, the upper left and the lower right point of the image. Next, we convert the geocoordinates to the pixel coordinates in the image. And here we including the subset array, the upper left X coordinate and Y coordinate, and the width and height of the part of the image we want to extract. So here, as you can see, the subset of the new, the subset we want to read begins in 2999 column, 3930 row, and has 1660 pixels width and 1998 pixels height. We're going to read our dataset with the function read as array. The arguments of this function is x of, which is the column, the pixel column, the image column to start reading at. The default value is 0 when we want to read the whole image. Y off is the row to start the offset, in other words, and the default value is 0. Win excites the number of columns to read. The default is to read them all. Similarly for the Y dimension, to the number of rows to read. Also buff X size and buff Y size, the number of columns and rows respectively in the output array. Here in this part of the tutorial we don't need to use it, but next you will see that these two parameters might be very useful if you want to resample your data while you're reading them. So here we have defined a function to extract the bands we need to read. We open the subdata set required. We get the number of bands stored in the subdata set and the description for each band stored in its subdata set. And we read it with the read as array function. And here we have defined the arguments of the function based on the subset computed above. So here you see how we extracted the red, green, blue, and near bands and near infrared bands from 10 meter subdirectory, and you see that the dimensions of the band extracted are correct, are the same like those we computed here. And we continue with an example of making a true color composite. Here we have a function to remove outliers based on 5 and 95%. And here we stack the three bands, red, green, blue, to make a true color composite, which is visualized here. And next we want to read the scene classification layer, which is available in subdirectories for 20 meter and 60 meters. Because when we computed the subset, we used the 10 meters transform. We must pay attention here and put the half of the subset in this component, since we have a 20 meters dataset instead of 10. It is the same procedures like the one discussed before. And here we try to read the scene classification layer and resample it to 10 meters at the same time, with where we define the buff X size and buff Y size as to be like the dimensions of a dataset with 10 meters. So the scene classification layer, the pixel for in the classification layer will be split half, but the value will remain the same because it includes categorical data, and we don't want to, with the resampling, to change the values. Here you can see the visualization of the classification layer, which includes cloud shadows, vegetation, water, and thin cirrus, which we will use them to mask out cloud cover pixels, or pixels which are considered to include erroneous values. Next, we continue with the normalized difference vegetation index, which is computed as the near infrared minus the red band, divided by the sum of near infrared and red bands. Here is the command computed. We have to transform the arrays to float, because the values in the Sentinel-2 dataset are stored as integers. And next is the command to mask out the cloud cover pixels and all other pixels that are considered to have bad values. And last, it is the results the masked out NDVI result. The white regions are masked out, so they are cloud covered pixels. And here it's the commands to store the results. We name the output as ndvi.tiff. We define the size of the raster, which is the same as the based on the subset defined for the 10-meter dataset. The transform is defined, we get it from the 10-meter subdirectory. The same is also for the get projection. And with the write array function, we write the results to the NDVI TIFF raster. Next, we continue with the normalized difference moisture index, which requires bands from two different subdirectories. Near infrared has 10-meter spatial resolution, and shortwave infrared has a 20-meter spatial resolution. So we have to resample the near infrared band to 20 meters. So we extract again. We get the bands and extract a small subset. For the 10 meters, we use the subset computed above. And for the short wave, we have to use the half dimensions since we have 20 meters spatial resolution. Next, we resample the near infrared band to 20 meters with the SkyPy function zoom, which is a spleen interpolation method, and we use the default, the polynomial order used is 3, it's the default value. Here we see the dimension, the new dimension of the near infrared band, and again. Here we have the command to compute the normalized difference moisture index and how we mask out the cloud cover pixels. Here you can see the final result. And again, how we store the final result. Here, as you can see, we have the half dimensions from the previous result, since we have a 20 meter spatial resolution. We define a new geotransform with 20 meters resolution, and we write the final the array compute the masked NTMI in the raster with the write array function. And this is the end of this tutorial. So now can we continue with the Q&A session, your questions?
Hi, Maria. Thank you for your tutorial. I would like to ask you a question. You do the cloud filtering just with the simplification, right?
Yes.
Is it high in the accuracy, this method, or we should choose some other available methods like cloudless and stuff like that?
Yes, here I just wanted to make a demonstration how we can mask out erroneous pixels. But yes, you can use a more precise method for cloud detection and use it.
And the question is derived on, will it have some conflicts on this with either cloud coverage or any libraries that you used in your tutorial, if we use another possible cloudless filter?
No, you can use the same. No, it will not be any conflict because I don't use. It's just a list comprehension. It doesn't. So if you store your results from any cloud detection method in an array, it will work. It's not
Okay.
something case specific.
Okay, thank you a lot, Maria.
Thank you.
Hi, thank you for your tutorial. I have already put my question on the chat, but I can also speak it out loud. So my question is mainly regarding the post-processing you have done regarding the Sentinel-1 data. Is the post-processing the same for all variables, or is like variable per variable post-processing?
Yes, the processing I described for Sentinel-1 is for creating backscatter analysis ready data. It is a standardized process which is considered to be useful for most applications requiring SAR data. But for vegetation optical depth, I think it might be a different processing. So I will search and give you a more precise answer to your question when I'm sure. Because
okay, that will be so kind of you. Okay, thank you.
You're welcome.
Hi, Maria. This is Claudia from IT. Thank you very much for the tutorial. I have some questions from the Sentinel-1 tutorial, and it's mainly because I've never used Sentinel Data, so perhaps they are a bit silly. The first question that I have is regarding the subsets, that we have to specify the subset in pixels, and that one is fine. But yes, regarding the height and the width,
yes,
how, like, are they standard? How do we define them? Because that one was not too clear to me.
Yes, this part, when we don't have the reference data, is that we have to guess the subset. There's not a strict way to define the origin of the subset and the height and width. Is with visual inspection, most of it.
Okay, but do we have like a range, more or less, to start with, like a minimum and maximum value both for height and width?
No, it's based on your area of interest. If it's large, you have to guess if the defined subset covers the area of interest.
Okay, thanks. And also, at some point, I saw that you were showing the Snap application, and I think it was when you were doing the correction, if I'm not wrong. But does it mean that we also have to download that one, or can we do everything through Python?
Yes, everything is automatic. Everything required is downloaded automatically.
Okay, because I saw that there was like a screenshot of another application, the Snap one.
Yeah, yes, this was more You mean this?
Yes, that one. Yeah.
This is the snap interface. In order to run all the commands here, you have to install this program. There is a snap.
Okay, so outside of Python, of course.
Yes.
Okay.
This information can be found elsewhere, but I saw example where you can find this information here. You can search it on Google and find the well-known text for the projection you want.
Okay. Thank you very much.
You're welcome. Other questions? So the Jupyter notebooks will be, we will send them to you to test them. And if you have any other questions, you can send me an email and answer to you. So if we don't have any other questions, we can finish here. So have a nice remaining day, and bye.
Bye, Maria. Thank you.
Thank you very much. Goodbye.
Thank you. Bye.
Bye-bye.